All right, welcome back to the Piezo SHOCK Show, episode number 67. Today I'm going to be talking about a very interesting topic, which is the difference between implicit and explicit modeling when you're doing simulation of ultrasonic transducers. We know that piezoelectric materials, they're inherently, to fully encompass their physics, it requires electrostatics, it requires that piezo coupling to the mechanical elastic domain. And in some cases, you require acoustics, but today I'm just going to be speaking about electrical and mechanical modeling. Um, so in a pure electrical domain, you're never going to model your piezo and finite element analysis because at the end, you want your piezo to oscillate. You want your transducer to oscillate. So the oscillation is what you're looking for. So when you're doing simplifications, you can simplify the front end. You can't simplify what you're actually trying to get, which is the oscillation. Which is why I just had a webinar on modal analysis, what I could actually calculate. Using only elastic methods, I could calculate a lot of the things that perhaps folks only thought they could do using electrical multiphysics analysis. But what are the differences and what are the benefits of using um, uh, implicit versus explicit piezo modeling? So implicit is, well, explicit is where, yeah, you have your voltage applied, you have your piezo oscillating, you have your charge and current generated, you have the electrical boundary conditions affecting the stiffness directly of your transducer. You have anisotropic properties that are utilized. Implicitly using applying piezos is, well, we don't have any voltages applied. If you do a harmonic analysis in this case, um, you are going to be applying a force at the faces of the piezo. You're not going to be applying an actual voltage. So there you have the kind of stand-ins for that analysis. You can still do optimization in those cases, but you do lack the direct calculation of things like impedance. So in which cases do you have to, absolutely have to use explicit modeling of your transducer? Of in the multi-physics domain, you can't get away from not doing it. um, I would say in a case where you need to be very precise on the final impedance values of your transducer. Now, this will also take other experimental values and a lot of history and experience, but if you want to be very precise and you don't want to design things more than once, like you have to get it right the first time, which is kind of ridiculous in my opinion. You usually at least will have one iteration or a few iterations in your transducer, or if not more. But if you really want to get it right the first time, which will save you a lot of time, especially if you have a driver which is already built. If you already have something from a previous device, you know what you want to work with, you know the power levels, you want to really have your whole system optimized from the get-go. In that case, you need to have multi-physics simulations. The other case is where you want to really know how defects and changes in your transducer will affect the impedance. Will change the output for it. So, for example, if you have like weaker you have weaker bonding in certain interfaces, how that's going to affect all the different modes, because the resonances and anti-resonances and how they'll all play together. um, it's not as simple as just assigning an open circuit and short circuit boundary condition. They're properties. There are actually anisotropic properties. There are the extensional properties along the 1 and 2 direction. Their Poisson's ratios are interacting. Their thickness direction. So where you actually have more complex oscillation patterns in your transducer than not just some axial device. In that case, you will need to model your piezo explicitly. Anisotropy is important, and also how those properties will then be constrained and affected by the electrical boundary conditions applied explicitly. Um, let's think of other areas where you need to model capacitance, where you're looking to compare your capacitance of your transducer. That's going to be important there. Um, I think where you want to know your effect directly on your electrical parameters, um, like you have a load, you have a loading function, you have a load, and you want to understand how that looks in the impedance spectrum. The other case is where you want to have precise alignment, well, as close as possible between your experiment and your simulation. You need to have multiphysics analysis there, because that's going to provide the impedance response, which is typically what we use to align experiments and finite element analysis. Basically, if you align those two, then you know your energies are very similar between your finite element analysis and your simulations, which gives you a lot of confidence. Now, if you just look at displacement, like, okay, this displays 30 microns at resonance, so ours will displace 30 microns at resonance, it's not really possible to align the two very well. But the impedance response from your electrical analysis can give you a lot of information that you want to put back into your finite element model, which you're going to align using you're going to align that using your impedance response that you would get from your multiphysics simulation. The other case is where you are modeling a sensor. That is going to be important to model your charges developed. Now, a lot of times I just speak about actuators, power transducers, but if you're modeling an energy harvester, or if you're modeling a sensor, you will definitely need to know that behavior. If you are working devices higher than 100 kilohertz, it's almost for sure that you need to do explicit modeling. If you do have a resonant style device, not just a pulse echo device. If you do have a resonant device, just because as you go to those higher frequencies, you'll have a more dynamic nature to how the oscillation is not going to be simply in one direction. There are going to be other material properties involved, which will be impacted uniquely by those levels of oscillation. The other reason why you'd want to have multi-physics simulations versus just an elastic simulation is a kind of a practical demonstration show and tell reason, is that you want to, when you're explaining to somebody how the device works, you don't want that to be different than how you model it, because that can get confusing. So it is useful to model your device the same way as you actually build and test it, because it just makes more sense flowing forward, and you may not miss a huge portion. Now, when you're just optimizing a device, it's not a risk. But when you are building a new device and you have absolutely no idea how it's going to oscillate, you want to have a multi-physics simulation, so you have a micron level, that you have a basic idea that your device is not going to be a nanometer displacement. It's going to be the micron or tens of microns. So you get a more clear feeling about that from your multi-physics simulation. Modal analysis is typically not a multi-physics simulation, although, because you do specify your boundary conditions. So that I think that I take that back. So if you specify your boundary conditions, you will have that impact from anisotropy, the boundary conditions associated with the elastic properties. But it's less critical at that point. But definitely for harmonic analysis, high frequency, and not to mention, looking at more exotic things like single crystal. So the differences between explicit and implicit are not as great as you would want to imagine. But when you want to reduce the number of iterations, it can be important. But if you do have a predicate device you're starting from and you're simply trying to optimize, it is more simple and straightforward to go with implicit modeling. But if you want to demonstrate to others, which is what engineers we're constantly trying to sell our work to our colleagues, to our clients, to model your transducer in the same way that it's actually fabricated is also powerful. It ensures you're not missing an item. It also gives you more specific numbers, like this is the impedance level, especially if you have good experimental data to help inform the modeling parameters. And you know how all that's done. If you don't know how it's done, you can contact your friendly local ultrasonic transducer consultant, Hussein Shakani at Ultrasonic Advisors. But if not, good luck. I know you can do it if you just work hard enough. All right, so that's been episode number 67, talking about the difference between explicit and implicit piezo modeling.